Another example independent of the previous Maclaurin series that we obtained is the following. Let us find the Maclaurin series for f of x equal to 1 plus x to the p, where p is any fixed real number let us assume that p is not 0, otherwise this is a boring function. It is just constant. Let's say p is not 0. Okay, so let us remind ourselves the formula for the Maclaurin series. Our goal will be to show that f of x is the sum f kth derivative at 0 divided by k factorial times x to the k. And then, once we have established the formula for Maclaurin series of this function, let us also find its radius of convergence. Okay, so clearly we need to determine derivatives of f of all orders and then evaluate them at 0. So the 0th derivative of f is f itself, so it is 1 plus x to the power p. The first derivative is, in order to differentiate this, I need to use chain rule. First, I differentiate the outer function, which is the power function, and then I need to multiply by the derivative of the inner function, which is 1. So this is the derivative of f. The second derivative is, again, I will differentiate the power function using chain rule, which gives p times p minus 1 times 1 plus x to the p minus 2. Then let's say the third derivative is p times p minus 1 times differentiating this power gives me p minus 2. And then I have 1 plus x to the power p minus 3. This sequence can be continued. And then the kth derivative, which we need to compute, will look like so. It will consist of the product p times p minus 1 times p minus 2 and so on. How many factors will we have here? Well, each differentiation adds a factor. We have performed k differentiations, so there will be k factors. And the last one will be p minus k plus 1, because the first one was p minus 1 plus 1, the second was p minus 2 plus 1, and so on. This is the last factor. And this product will be multiplied by 1 plus x to the power p minus k. Great. Now, in order to use these derivatives in the formula for the Maclaurin series, we need to evaluate them at 0. The 0th derivative at 0 is 1 to the p, so that would be 1. The first derivative at 0 is p times 1 to the p minus 1, so that would be p. The second is p times p minus 1 times this expression, which evaluates to 1. The third is p times p minus 1 times p minus 2, and so on, all the way to the kth derivative, which at 0 will evaluate to the product p times p minus 1, and so on, all the way down to p minus k plus 1. So we obtain that the Maclaurin series for f of x equal to 1 plus x to the p looks like so. We have sum from k equals 0 to infinity. Then the kth order derivative evaluated at 0, which we have just computed to be p times p minus 1 times p minus 2, and so on, down to p minus k plus 1, divided by k factorial, multiplied by x to the k. So this series has a special name. It is called the binomial series. So the reason it deserves a separate name is that for p equal to some integer number, say n, this infinite sum becomes finite, because when k is equal to n plus 1, let's say as only terms up to degree n. So this infinite sum will be n, n minus 1, n minus 2, and so on, times n minus k plus 1 over k factorial times x to the k. And so this is the expression we will have for 1 plus x to the n. So when p is an integer, is a positive integer, then this is a finite sum. This is just a polynomial. And so that is why the right-hand side, this infinite sum, will only have terms up to degree n. This being a polynomial of degree n, you cannot have higher degrees in the right-hand side. And in fact, as soon as k is equal to n plus 2, this product over here, let's see, no, sorry, as soon as k equals n plus 1, this product over here contains a factor like this, n minus n plus 1 plus 1, which is equal to 0. And all the terms starting from k equals n plus 1 contain this factor. So all the terms starting from k equals n plus 1 contain this factor, which is 0, in the numerator. So we obtain the expansion for 1 plus x to the n is equal to the sum from k equals 0 to n, because kn plus 1 already is 0. And the product we have here as the following form. Divided by k factorial times x to the k. So this is the binomial formula. Now, I'm missing the dots for all the missing factors in the middle. And so this here contains finitely many terms, and this is known as the binomial formula. Which explains the name binomial series for this infinite series. So once again, we have the expansion 1 plus x to the p is equal to the sum k from 0 to infinity. In here, by the analogy with the binomial formula, we will introduce a special name for this expression. We will call this binomial coefficient, because for the integer case, we can write this finite sum as n factorial divided by k factorial times n minus k factorial times x to the k. And this expression is known as the binomial coefficient. And so by analogy with the final case, we will say that this here is the binomial coefficient, denoted like so. We say binomial coefficient p choose k is equal to p times p minus 1 times p minus 2 and so on, p minus k plus 1 divided by k factorial. So notice all I did here was I just took the expression that we had for the kth coefficient in our expansion, and I introduced a special notation for it. I said, let us use this shorthand for the entire coefficient, and then it is multiplied by x to the k. So this here is this generalized binomial coefficient. P can be any real number, and k is an integer. The way to read this is p choose k. Okay, so we have obtained an expansion for this binomial expression. Now, let us answer the second question of this example, namely, what is the radius of convergence of this power series? So we use our familiar tool here, the ratio test. So we will need to look at the absolute value of the ratio ak plus 1 over ak, which is, so first the expression for ak plus 1. So here is the coefficient for ak. So I will need to write the following here. I will have p times p minus 1 times p minus 2 and so on, right? Here, this being the ak term, I go down to p minus k plus 1. So for the ak plus 1, I will go to p minus k plus 1 and then one more term, p minus k plus 1 plus 1. This is, of course, simply p minus k. And then it is divided by k factorial. Oops. And multiplied by x to the k. Now it looks I will need to rearrange my terms a little bit. So let's say this entire thing is my ratio. So I have ak plus 1. By the way, this reminds me that I should have placed k plus 1 in here. So this is in fact k plus 1 factorial, and this is x to the k plus 1. Okay, good. So this entire numerator is the term I have for ak plus 1. Denominator will be simply the expression for ak. So I know how to write that. It's p times p minus 1 times p minus 2 and so on. And this time I only go down to p minus k plus 1. Great. Divided by k factorial multiplied by x to the k. So this entire expression in denominator is my ak. So let us pull this up again and compare. You see that all I did was I took this expression, I replaced k with k plus 1, put that in the numerator, and then just took it without any changes and put it in the denominator. Good. Let's see what will cancel. So first of all, I can get rid of x almost entirely. Then you see that all of these factors, but the last one, occur both in the numerator and in the denominator, so they will cancel as well. So the first step will be to rewrite this as p minus k for this numerator divided by k plus 1 factorial multiplied with x. So this is the numerator after cancellation, and then divided by 1 over k factorial. Everything else in the denominator has cancelled. This, of course, is simply saying that I have absolute value and then p minus k divided by k plus 1 times k factorial times x times k factorial. Instead of dividing by 1 over k factorial, I'm multiplying by k factorial. And this is after cancelling out the k factorial. P minus k divided by k plus 1 absolute value multiplied by absolute value of x. Alright, so this is the value of the ratio for which I must compute the limit. So my next step is to take the limit when k goes to infinity of this expression. Times absolute value of x. Observe that I have k to the first power here and here. So I can rewrite this as limit k goes to infinity p over k minus 1 divided by 1 plus 1 over k. Of course, this goes to 0 and this goes to 0 as well. And I have minus 1 divided by 1 under the absolute value. Because of the absolute value, I end up with 1. And then it is multiplied by absolute value of x, which is independent of k. And so this finally is just equal to x. Because this is the output of the ratio test, I must have absolute value x less than 1 to have convergent series. So you see that the series converges when absolute value x is less than 1. If you recall our discussion of computing the radius of convergence using the ratio test, you would have to rewrite this in the form x minus a, which is in our case 0, minus is less than r. So this means that r in this case is equal to 1. And so we can conclude that 1 plus let's say 1 plus x to the p is equal to the infinite sum k from 0 to infinity, p choose k times x to the k when absolute value of x is less than 1. So this representation is only true when absolute value x is less than 1. And so p is any real. So in fact, if p is 0, this equality will also hold. If we assume that p choose 0 is always 1, regardless of the value of p. So I should put this here, we are assuming that p choose 0 is 1 by definition. Otherwise, it is not clear what happens in the numerator. So with this assumption, this representation holds for absolutely any real number. And in this representation, p choose k is defined as p times p minus 1 times p minus 2 and so on times p minus k plus 1 divided by k factorial if k is at least 1, and p choose 0 will be by definition 1. And so this power series representation for 1 plus x to the p is what we will refer to as the binomial series.